So actually, all these pHs we can get by just doing the standard method, which is just solution dilution, strongest acid, strongest base. Some of these we can get a lot quicker, you know, if we just realize what points we are. But let's say I want to get the number of milliliters to get to a certain pH. So what pH do you like to calculate? 3.7?
First buffer zone?
First buffer zone would be similar to monoprotic that we did earlier. Let's go with maybe something in the second or the third buffer zone. 5.0? All right. pH of 5.0. Okay, let's try that. So if we wanted a pH of 5.00, you know, how many milliliters would we have to add to this? Here. And so there's, you know, there's the long method, which we'll just go ahead and do it that way. The long method would be, you know, we don't know how many milliliters, but we know we're starting off with 10.00 milliliters of acid. It was 0.100 molar. And then we're going to add some amount of base. What should we call that? It's 0.100 molar sodium hydroxide. What do you want to call that? X milliliters. Okay, I'm going to call it Z plus Z milliliters. Because sometimes we use the X for the ice tables. It's called Z. And so the first step is to do the solution dilution. So, you know, we're going to end up with 10.00 plus Z. And we can figure out the new sodium hydroxide concentration. It's going to be 10.00 plus Z, Z over 10.00 plus Z, times 0.100. Figure out the citric acid concentration. It's going to be 10 to a 10 plus Z dilution. And we set up the strongest acid plus the strongest base. Here's where we have to know something for the ice table. The strongest acid is going to be citric acid. The strongest base is sodium hydroxide. We do this one step at a time, even though we already know we're in the second buffer region. But we're going to form the dihydrogen citrate and water in the first step. And so we're going to call these the initial concentrations before reaction. Initial, that's initial. And so the H3CIT initial will go here, sodium hydroxide initial will go here, and this will be 0. All right. Since we're in the second buffer region, that means we've neutralized the first proton completely. And so that means that this is going to go to 0. Right? And that means we'll have some excess sodium hydroxide left over. How much excess? Well, you know, we're going to lose this amount. That means we're going to lose, you know, the same amount here. And then we're going to gain this amount here. And so the sodium hydroxide after step 1 will be the sodium hydroxide initial minus the initial concentration of the citric acid. Okay, that would be the sodium hydroxide after step 1. The dihydrogen citrate after step 1 would be the same as the initial concentration of citric acid. And so we would know, we'd have to know this, you know. All right, so we have strong base and amphoteric. The amphoteric is going to be the strongest acid. So we'll go on to step 2, which would start to neutralize the second proton. And so this would be the dihydrogen citrate plus the sodium hydroxide, which is going to yield the monohydrogen citrate plus water. Okay, then we're going to have to know this next step too. in the next step, we're in this buffer region number 2. The buffer region number 2 means we haven't completely neutralized all the dihydrogen citrate. We've partially neutralized that to form some monohydrogen citrate. And so the limiting reagent here is going to be the sodium hydroxide. And so the concentration here of the dihydrogen citrate will be the same as our initial concentration of citric acid. The concentration here of sodium hydroxide will be, yeah.
2 times H3CO2. Oh, the equivalent sign.
No, just minus H3.
Yeah. That was down to the E.
Initial. This is going to be 0 here. And so we're going to completely consume all this, right? All the sodium hydroxide has to be consumed. How do I know that again? Because this is not excess sodium hydroxide, and I've only partially reacted. This is the initial starting acid here, and I've only partially reacted it here. To completely react it, I'd have to go all the way to here. And so I know I only partially reacted my dihydrogen citrate.
You only know that because you're looking for a pH of 5.
Right, I know that because I'm looking for a pH of 5, which means I'm between here, which is all acid, and here, which is all base. I have a mixture of acid and base. We could divide it like this. You know, this would be 100% dihydrogen citrate, 0% dihydrogen sulfate citrate. This would be 0% monohydrogen citrate, 100%. We're in between, somewhere in between those. And so I have to lose all my sodium hydroxide, so this is going to go down to 0. That means my sodium dihydrogen citrate must be the initial concentration of citric acid minus this. So it's going to be a minus the sodium hydroxide initial. Yeah, minus the citric acid initial. So this would be a minus times a minus, which would be a plus. So I'll have 2. So this is going to equal 2 times the minus the NaOH. Okay, just to simplify that a little bit. I just multiplied by -1, and then just added these 2 terms. Just simplified it. All right, the amount of monohydrogen citrate I'm going to generate would be equal to this. It would be sodium hydroxide initial minus the citric acid initial. Right. All right, so far this is what I have. And so I need some more information. The more information I have is, well, the sodium hydroxide is going to be 0. So get this mix of acid and base. They're conjugates of each other. In other words, this is a Henderson-Hasselbalch buffer. So I need the ratio of base, which is the monohydrogen citrate, to acid to be a certain amount that gives us the correct pH. So I'm after a pH of 5.00. This is going to equal the pKa of what acid? Yeah, in the second buffer region, the acid would be H2CIT minus. And so this is going to be the pKa of H2CIT minus plus the log of the base. The base is going to be HCIT2 minus divided by the acid, which is H2CIT minus. And so the pKa, what was the pKa of dihydrogen citrate? 477. pKa is 477 plus the log of that. Subtract 477 from both sides, so I'm going to get 0.23 is equal to the log of the ratio, which means the ratio of HCI2 minus to H2CIT minus
1.698 to 1.
is 10 to the 0.23, which is, what is it?
1.698
1.698
to 1, or whatever.
to 1, right. And then what I'd do is I'd substitute these. This is after step 2. And so here, the dihydrogen citrate concentration, or actually monohydrogen citrate in the numerator. The monohydrogen citrate concentration after that step is sodium hydroxide initial minus citric acid initial. And so the numerator, I'm going to get the sodium hydroxide initial minus the citric acid initial. And down below here, I have the dihydrogen citrate, which is going to be 2 times the citric acid initial minus the sodium hydroxide initial. And then I would substitute, right, and then solve for Z. And so substitute and solve for Z. And Z will give us the number of milliliters that's required. This is the long way. There's a much shorter way of doing this, which we can skip a lot of this work. So I'll let you finish this one if you want, or you could just do the short method of doing this. So let's do the short method of doing this is, let's divide that buffer region. So the buffer region starts at 395 and then ends at 559. And then we're going to look at the range. At the start, at 395, I just have H2PO4 minus. At the end, I just have HPO4 2 minus. And so at the start of this, I have this acid. It's going to be 100% H2PO4 minus. But by the end of this, I should have neutralized all that acid, and I should have 0% H2PO4. I'm sorry?
Citric acid. Oh, you're using phosphoric all this time. I didn't even recognize that either.
I'm doing it different. You can tell I usually use phosphoric acid, but I wanted 3 equivalence points. Well, phosphoric acid wouldn't have given it to me. So anyway, dihydrogen citrate to over here, I would have 0% of the base, which would be HCIT 2 minus, and 100% of the base HCI2 CIT 2 minus. All right, and then I can have whatever. This is just a continuum of values. And so the pH of this is going to be based on the base to acid ratio. And so the pH is just going to equal the pKa plus the log of the base, which is going to be HCIT 2 minus, over the acid, H2CIT minus. this ratio. Yeah. Except at the extremes, you know, at the start, we can't use the Henderson-Hasselbalch because the base would be 0, and over here the acid would be 0. So at the extremes, but anywhere in between these two, we can do it, even if it exceeds the ±1 range. And so right in the middle, we know we have a 50-50 mix. So if we have a 50-50 mix, you know, it's 50% this, 50% that, that would be the log of 1, which log of 1 is 0, which means the pH is equal to pKa. So that's what we have here. But let's say we've neutralized 25%. If we've neutralized 25% of our acid, then we have 75% remaining. Sorry, it should be 75%, which means 25% of that was converted into base, right? And so what is the ratio for this? Well, the ratio looks like it's going to be the pH is equal to the pKa plus the log. Now the base is going to be 25%, right? The acid is 75%. If we've neutralized 25% of our acid, we call that the 1/4 equivalence point, correct? And so that would be 1/4 of the equivalent volume. And in other words, the 1/4 equivalence point would occur at how many milliliters? Well, if this is 10 milliliters total, then the 1/4 of 10 milliliters is 2.5 milliliters. And we're starting at 10, so 10 plus 2.5 milliliters would give us 12.5 milliliters, right? 1/4 equivalence point. And so, well, this turns out to be pKa minus 0.477, log of 1/3. And so what we're going to look for here is this. This numerator term would be the equivalence point here. What part of the equivalence point we have. And so this will be 1/4 equivalence point, that ratio. All right, so what we're going to do here is this. We're going to look. If we want a pH of 5.00, then this is going to be the pKa plus the log of the ratio. And then we determine the ratio is going to be what? The ratio of monohydrogen citrate over dihydrogen citrate is equal to
5 minus pKa. 10 to the 5 minus pKa.
well, no. You just calculated. What was the number?
Oh, for the pKa of
1.698.
1.698? 1.698. And so where does that lie on this line here? Well, if this is the ratio, then we'll call it 1.698 over 1. Well, how does that relate to this? Well, this means we have 1.698 parts of base to 1 part of unreacted acid. And so in other words, it comes out to this. From this, we'll get the total parts. Actually, I can erase this part here. there'd be 2.698 total parts. And so that means 1.698 out of 2.698 were converted into base.
You want a decimal for that?
What's that?
You want a decimal for that?
No,
You need to
No.
research.
not yet.
Okay.
And then that means one part was unreacted out of 2.698. This remains as unreacted acid.
How do you get the 2.698?
I just
Total
add
parts.
the parts here. All right, now give me the decimal for this. 0.698? No, it's got to be less.
It's 0.6293.
0.6293, so 62.93% reaction. So we have 62.39% or 93% reaction from here. That means what was unreacted is going to be 37.17% unreacted. So, in other words, we're at the 62.93% equivalence point. Should be here. And so, well, how many milliliters is that? Well, 100% is 10 milliliters, right? And so what is 62.93% of 10 milliliters? That would be 6.293 milliliters.
But you have to add that to the first 10.
Yeah, then we have to add it to the first 10 because it's 6.293 milliliters from here.
Well, it's 10, so from there to there.
Yeah, and we're starting at 10. And so this is going to be altogether, that's 16.29 milliliters. 16.293 milliliters. Okay. All right, so that's a shortcut method. And so the shortcut method, we can get a bunch of these quickly. And that is, at the quarter equivalence point, it's minus 0.477. At the 3/4 equivalence point, it's plus 0.477. At the 1/11th equivalence point, it's minus 1, pKa minus 1. At the 10/11th equivalence point, it's pKa plus 1. What's that? Oh, is it? Okay. Yeah, you're right. 37.07. All right, so what is the 1/4 equivalence point here? So this is pKa minus 0.477. This is pKa plus 0.477. So at 22.5, pKa minus. At 27.5, pKa plus, right?
Wait, why is it pKa plus 4.77?
Okay, I'll take a look at it. Well, what equivalence point is this? This is the 3/4 equivalence point 2, right?
Mm-hmm.
And so there's two ways of doing this. The pH is equal to the pKa plus the log. Well, that means 3/4 of it is reacted. So 3/4 reaction, 1/4 left over.
75.25.
Yeah. Or, you know, this is pKa plus the log of 75% reaction over 25% unreacted. And so in other words, it comes out to log of 3, which is plus 0.477.
Oh, okay.
All right.
Yeah.
Okay, then, so we should know those. So this is going to be the pKa plus 0.477. And so it's pKa minus
Nice.
0.477.
Actual numbers.
And then over here at the 111th, what is the 111th equivalence point? How many milliliters is 111th? Well, that's 111th of 10 milliliters. 111th of 10 milliliters would be 0.909, right, milliliters. That's going to be the pKa minus 1. And that's 1/11th of the equivalence volume. And so this is equal to 1/11th of the VEQ. The equivalent volume is 10 milliliters. And then over here at the 10/11th equivalence point, is going to be 909 milliliters. And it depends on where we start. You know, if we're starting at 10, so this would be 10.9. This would be 19.09. But this would be pKa plus 1. So the buffer region, you can use this. And so what you have to do is you have to figure out the relationship between where you are here and what the percent reaction is and how that relates to the ratio here. And so this is probably the most confusing connection to make is that. Okay. Now, what if we're outside the buffer range? Then we can't use any of this. Right. And so if we're outside the buffer range, let's say I want the pH of 10.50, you know, how many milliliters of base do I have to add? Well, 10.50 is in the excess NaOH. So how would I calculate that for the excess NaOH? Well, the way I'd calculate it would be I have to start from the beginning and do the long method. That is, we start off with 10.00 milliliters of citric acid. In here we're going to add Z milliliters of sodium hydroxide. And then we do the solution dilution. And then we'd set up the ice tables. And so you'd have to know how far we have to go in the ice table. And so you would see that we're in the excess base region, and we don't just go straight there. We'd have to start over again at the very beginning and work through it. And so after I do my solution dilution, I'll get my initial concentrations here. What will I have at equilibrium after step 1? Tell me what is my H3CIT after step 1?
Should be
0. This has got to be 0. This is going to be what?
Plus H3CH. Oh,
Yeah.
Sorry, minus the plus the other side.
And this will be,
Plus H3CH.
okay. All right, then we'll go to the next step. We have strong base and amphoteric. So the amphoteric will act as the acid. Strong base will start to neutralize the second proton. And so my initial dihydrogen citrate will be the initial sodium hydroxide. This will be 0. Okay, tell me at the end of this step, what am I going to have left over?
No NaH2CIT.
Okay.
That's going subtract from that other nasty number.
This will be what?
NaOH minus 2 H3CITs.
Yeah.
And then plus on the other side.
That's right. All right, what's the next step? What should I write out? Well, what do I have left over? I have strong base and amphoteric. The amphoteric will act as the acid. In other words, I can neutralize that last proton. And so Na2HCIT plus another sodium hydroxide. We have left over sodium hydroxide. This is going to produce sodium citrate plus water.
Still have the H3CIT concentration.
So the HCIT will be
H3CIT.
H3CIT. The NaOH will be
Minus 2 H3CIT. 0.
0. Okay, at the end of this step, what am I going to have left over? Well, okay, what's my Na2?
Left over. Right.
What?
You're still going to have NaOH left over because above 7?
Yeah, I'm going to have NaOH left over, so this is going to be
0.
0. And so I've neutralized the last proton, now I have excess sodium hydroxide. So this is going to be
Minus 3 times.
minus 3 times CIT, and the citric acid, citrate, sodium citrate will be H3CIT. Okay, so what am I left over with? I'm left over with strong base and weak base. And so I have to figure out all my hydroxide. This is a base solution. So what are my hydroxide producers? Well, the strong base and the weak base. This is a tribasic base. So it's going to be KB1, KB2, KB3, and water, KW. All right, what should I do? Should I just worry about KB1 for this? Or should I ignore KB1? In fact, should I ignore all of them? KB1, KB2, and KB3 and KW? What do I want to do? Because that's going to dictate how I do the next step. So should the next step be, let's say KB for sodium hydroxide? Well, KB for sodium hydroxide is already hydroxide. And so hydroxide plus water yields water and hydroxide, so it doesn't change. And then I got to see, well, I'm going to add to it, right? And so should I do KB1 for citrate? Yes or no? No. Why not? We did it before. Shouldn't we do it again?
I don't know why.
Yeah, it's not significant. Before it was significant. We did KB1 and we were worried about KB2, but now we don't even care about KB1 because of the... Well, is it because of the KB? It was like 10 to the minus 4? No, it's because of the common ion effect, exactly. The common ion effect means that, KB1, I'm not even going to worry about that at all. And so, in other words, unless KB, if KB1 were big, like say for example, KB1 were 10 to the minus 2. If KB1 were 10 to the minus 2, I would worry about it, right? Because even though I have common ion, well, that's kind of a big KB, I expect some additional hydroxide. This would be exactly the same scenarios like H2SO4. H2SO4, you know, the first K is huge, right? And the second K is pretty big, 0.011, which leads to another 10% hydronium in sulfuric acid, right? And so if this KB1 were like 10 to the minus 2, then yes, I would do it. I would figure out. But this KB1 is like 10 to the minus 4, I'm not even going to bother. Because the common ion effect means I'm probably going to get negligible amount of additional hydroxide from that. And so what I'm going to say is I'm going to say this. I'm going to say that the pH is dictated by the sodium hydroxide and not really any of the citrate is going to impact that. All right, and so the next step here is, well, if I know what the pH is, I can figure out what the pOH is. You know, the pH is, what, 10.5? That means the pOH is going to be 3.50. The pOH is going to equal, well, 3.50, which means the hydroxide ion concentration will be 10 to the minus pOH molar, which is going to be 10 to the minus 3.50 molar, which means the hydroxide ion concentration is going to be whatever that comes out to. And that's going to equal all the hydroxide from the sodium hydroxide. So this concentration of sodium hydroxide is the concentration of hydroxide I have. It's a 1-to-1 mole ratio of sodium hydroxide to hydroxide. And so this is going to equal the sodium hydroxide initial minus 3 of the citric acid initials, and then just sulfur Z. Right? And then we're done.
It came out to be 0.000031628, whatever.
Okay. Good, thanks. Just do that. All right, so these are the types of problems you'll encounter with the titrations. Are there any questions on titration?
Oh yeah, when you have excess acid, will HCl or ammonium determine the pH of the solution?
If you have HCl and ammonium mixed, then the HCl will, unless HCl is in very, very dilute. Let's say you have 6 molar ammonium, NH4 plus. Yeah, it all depends, because if the molarity of the ammonium was very high, and the molarity of the HCl was very low, then which one do you think is going to dictate the pH?
Ammonium.
Ammonium, because there's barely any HCl in there. But if the molarity
How about if it's comparable?
was significant, let's say you had 6 molar ammonium and 0.1 molar HCl, the HCl is going to dominate. Because ammonium has a Ka of 10 to the minus 10, and HCl's Ka is huge. And so even though we have 6 molar ammonium, we barely get any hydronium from that compared to the HCl, which would get a huge amount of hydronium from that. And so we can come up with little rules. Little rules of thumb are this. Rule of thumb. You know, if you have a strong acid, weak acid mixture, the strong acid dominates, right?
Yes.
Until you get an unusual scenario where...
What if one is 0.200 molar and another one is 0.100 molar?
Then they're both significant concentrations, and therefore the strong acid dominates.
But in the solution's magnitude, the ammonium dominates. Therefore, ammonium determines the pH of the solution. I don't know why.
What problem was that?
47 or something. Or 48. It's situation with ammonia and hydrochloric. That part.
All right, it's not 47 or 48. We'll take a look at that, and remind me tomorrow or the next day. We'll take a look at that problem specifically. All right. You know, in general, the strong acid dominates unless, you know, it's one of these unusual circumstances where you just don't have much acid. The same thing can be said of strong bases. You know, but there's a whole bunch of caveats. Like, for example, if the weak base is borderline strong, you know, like phosphate, if this were a sodium hydroxide, sodium phosphate mix, then yeah, phosphate's going to contribute. You better at least do KB1. Otherwise, you're going to be off, right? Because the KB1 for phosphate's pretty big. And so there are a whole bunch of little caveats to that you have to keep in mind. In other words, exceptions that you need to know. All right, so that's chapter 17. I want to start with chapter 18. Next, chapter 18 is the final chapter of these equilibrium type calculations. Chapter 18, we're going to look at some more K's. We're going to look at KSP. We're going to look at KSPA. We're going to look at KF and KSPF. Huh? Yeah, some 10. This is basically what they tell you. KSP deals with solubility. You know, the equilibrium in solubility is the equilibrium between, you know, a solid and its saturated solution. So it's how much solid can you dissolve in water, basically. And so the forward process, when the solid goes into solution, we call that dissolving, or we call it dissolution. When the saturated solution begins to precipitate out as a solid, we'll call that crystallization or precipitation. Usually we'll just use dissolution for the forward, crystallization for the reverse. So we've reached a dynamic equilibrium where we've dissolved the maximum amount of solid in water. But we don't have to dissolve it in water. We could try to dissolve things in acids and bases as well. And so when we try to dissolve things in acids and bases, that's going to show a pH dependence on solubility. And so this is it. KSPA deals with solubility and pH. pH is the power of the hydrogen ion concentration, or power of the hydronium ion concentration. And so in other words, we're looking at, you know, how acid impacts the solubility. This is KSPA. KF deals with formation of complexes. And so just a quick example, if I have copper 2 ions, this is what we call free ion. It's not complex with anything. But if I introduce ammonia to this, 4 ammonias will attack as ligands and form the tetraamine copper 2 ion, which would be complex copper. This is what we call KF. This happens in steps. All 4 ammonias don't attack simultaneously. And so normally, you know, what we have is this KF would be K1 times K2 times K3 times K4. K1 is the first ammonia attacking, and so we form the monoamine complex. K2 would be the second, and we form the diamine. K3 would be the third, trimine. K4 would be the fourth. But what happens is this reaction is so favorable that what we do is we'll just do them all together once, combined. We don't do it separately, because this is different than, let's say, if you have a polyprotic acid. If you have a polyprotic acid, each successive step becomes less and less. Yeah, but in this case it isn't. It's going to attack until it's finished attacking. And so normally we look at the formation as not these individual steps, we look at it as a whole, as a combined thing. And KSPF deals with solubility in the presence of complexing agents. So aqua regia is a KSP, actually, etc. Actually, there's variations, but aqua regia is an example of a KSPF. Well, actually, it's more complicated. Well, maybe not aqua regia. Let me do something simpler because aqua regia is more. Well, silver chloride solid. Silver chloride is what we call insoluble. What does insoluble mean? Insoluble means that less than 0.1 molar will go into solution. In other words, less than 0.1 moles of silver chloride will dissolve in a liter. And that's what we call insoluble. Silver chloride insoluble. We also have slightly soluble. Slightly soluble means that about 0.1 mole will go in a liter. And soluble means greater than 0.1 moles will dissolve in a liter. This is according to your book and also the handouts earlier. And so this is all qualitative. If we want to be more specific, like I don't want to know if more or less, I want to know how much goes in solution. And so quantitative, we usually get from experiment. And so you could do experiment to measure the solubility. The solubility is equal to or defined as the max amount of solute that will dissolve in a given amount of solvent or and so the typical units of solubility are grams per milliliter of water, and so grams of solid, or molarity, moles of solute per liter of solution. And so we call this the molar solubility. This would just be the gram per mil solubility.
Why is it must be determined by experiment?
Why must it be determined by experiment? Ka, for example, Ka, must Ka be determined by experiment or can we do it theoretically?
Experiment.
Tell me a way to get a Ka from theory.
KW?
We could get Kas from other known Ka values, maybe in add-up equations, and do that. Does Kw come from experiment or does Kw come from theory?
Okay, where was it derived from theory? How was it derived from theory?
Okay, the ionization equation. Remember the hydronium minus times A minus over the HA?
Okay, how did this come from theory?
It came from theory because of the ionization equation for
The ionization equation, this equation,
came from experiment.
this equation is an empirical equation, which means it comes from experiment. So far, all we've dealt with are experimental values. That chart of KAs comes from experiment. Those are averages from a whole bunch of experiments. And so the same thing with the solubility. The solubility, okay, I want you to do this. I want you to tell me what the solubility of silver bromide is going to be using theory.
You can't.
Tell me how many grams will I be able to dissolve in 100 milliliters using theory? Are you going to do that? No, I mean, you get nowhere, right? Because it's going to be too difficult. Because what you have to do, in using theory, we're going to do all these calculations, lattice energy, hydrated ions, all this other stuff. And so oftentimes theory is just too much to deal with. And so we'll just do it. And so experiment is, my question was, why would you use theory? Why wouldn't you use experiment? That would be it. But the thing is, in order to use experiment, that means we have to do a measurement for every single salt. We want to know what its solubility is. And so if I want to know the solubility of silver chloride, I have to do an experiment. Well, fortunately, somebody's already done that for me, right? And so I've just used their data, and then I can make predictions. And so somebody calculated the solubility of this. And then what we can do is there's going to be a dynamic equilibrium here. This dynamic equilibrium is going to be dictated by the equilibrium constant, K. K is going to equal the activities of the products. So the activities are going to be close to the silver ion and the chloride ion concentration, divided by the activity of the reactant. The reactant is pure solid here, so the activity is 1. And so this would be it. This is called our KSP equation here. Now the KSP equation, the way we do this is we assume that nothing has dissolved yet. And so we just have pure water. We add the salt or the solid to pure water and then saturate it. And so we give it enough time. So this is going to be plus X molar, plus X molar. And so at equilibrium, we're going to get X molar and X molar here. Okay, what is X? Well, X we have to determine by taking solubility measurements. And so it turns out that the solubility of silver chloride would be the maximum silver chloride concentration we can get in water. This would be the molar. How many moles of silver chloride can I dissolve in a liter? Well, because of the mole ratios here, it's a 1 mole of silver chloride produces 1 mole of silver ions. And so this is going to be the same concentration of the silver at equilibrium, these are all in equilibrium, which is going to be the same as the chloride concentration at equilibrium. And so it turns out that X is equal to the solubility here, because the concentration of silver ion will be the same as the concentration of silver chloride that we can dissolve in water. And so X is equal to S here. And so in this particular chapter, what we're going to do is we're going to not use X here, since what we're going to do, sometimes we're going to use X, sometimes we're going to use S, depending on the question itself. And so in this particular chapter, we have a choice. The choice is this. We start off at 0 here, and we start off at 0 here. the choice is, this is going to be plus X or plus S. It's not always plus S. We have to look at the particular problem. But in this case, it's going to be plus S because we're going to dissolve the maximum amount of ions in solution here, the chloride. And so at equilibrium, we're going to get S molar and S molar. And so the next thing we do is we measure the solubilities. We measure the solubilities, and therefore we can get KSP, because KSP is going to just be S squared. And so you get the solubilities, and you measure it, and then you calculate the KSP. It comes out to 1.8 times 10 to the minus 10. 1.8 times 10 to the minus 10. Which means that the solubility must have been, well, the solubility is just the square root of that, which is going to be what? I'm going backwards here, but somebody figured out the solubilities to get the KSP. A whole bunch of people did that, and that's why we get this. This KSP comes from experiment. And this is an average of a whole bunch of experiments. And so what is the solubility?
1.3416
Molar. And so we can dissolve 1.3 times 10 to the minus 5 moles per liter, which is how many grams? Not many grams, right? Very, very little grams salt in a liter. All right, so the one of the main differences is in chapter 16 and 17 we only had quadratics, right? A whole bunch of different quadratics. But in this chapter, we're going to have much more complicated ones. For example, if we're looking at something like calcium phosphate, Ca3PO42 solid, and if we dissolve this, calcium phosphate's a ionic salt, and this is going to dissociate into 3 calcium 2 plus 2 phosphates. This is assuming ideal behavior, which we're going to assume for all of these. We're going to assume that the ions are just going to break apart when it's dissolved. And so when we look at the KSP for this, the KSP is going to be the calcium ion concentration squared times the phosphate ion concentration to the, calcium ion would be cubed. Phosphate ion concentration squared. Now the solubility is going to be tricky because the solubility is how many moles of calcium phosphate I can dissolve. And so the solubility of this would be the concentration of calcium phosphate in water at equilibrium. Well, calcium phosphate's up here, and so what we're looking at is, well, we got to relate this to the ions. And so if we relate this to the ions, then the solubility of calcium phosphate is actually 1/3 the concentration of calcium. That's because for every mole of calcium phosphate, we form 3 moles of calcium ions. And so this 1/3 comes from 1 mole of, 1 mole of calcium phosphate yields 3 moles of calcium. And so the 3 moles of calcium cancels out 3 moles of calcium and gives us calcium phosphate here. And so this is going to equal 1/2 the phosphate ion concentration. And so if we start off assuming nothing's dissolved here, so this is 0 molar, this is 0 molar, the change is going to be plus 3x, right? But we know that x is going to be the, in this case, this is going to be plus 3s plus 2s. And so at equilibrium, we're going to have 3s here and 2s here. And so the way that KSP relates to solubility is that the calcium concentration at equilibrium is going to be cubed. So this is going to be 3s quantity cubed. And the phosphate concentration is going to be squared. This is going to be 2s squared. And so this is going to be 3 cubed is 27s cubed. 4s squared, which is going to give us 4 times 27, would be 108, right? S to the 5th.
Yeah.
And so this is the relationship between KSP and S here. Now, the reason we want KSP is so we can do other calculations quite easily with the S. And so in the first part of this chapter, we're just relating the KSP, which is, SP stands for solubility product, with solubility. This is the first part. And so either we're given a solubility and we calculate KSP, or we're given a KSP and we calculate solubility. Those are the two types of things. The KSPs are compiled into a table in Appendix D in Chapter 18.
There's a lab for that in the lab, in the class.
Yeah, except we're not going to do that particular lab. We're not going to do that particular lab, unfortunately. Right. Now, the next thing is going to be precipitation. So let's say I have a solution. What was the solubility of this? The solubility is quite low, right? And so let's say I have 0.100 molar silver nitrate. Silver nitrate's soluble, so 0.100 molar is no problem. And then what I'm going to add to this is I'm going to add some sodium chloride. And so what I'm going to do is, there are two ways you deal with these types of problems. One, you have to do a solution dilution. Or two, we don't do solution dilution. And so in the case where we don't do solution dilution, let's say I made the solution 0.100 molar silver nitrate and 0.200 molar sodium chloride. And so what's going to happen? Well, silver ions, like chloride ions, and will form a precipitate. The way we deal with precipitation in Chapter 18 is we'd like to do this. We'd like to say, okay, the silver ions will react with the chloride ions to precipitate out silver chloride. That's the way we'd like to do it, but that's not the way we're going to do it. The way we're going to do this is we're going to write out the KSP equation. Silver chloride is going to go to silver ions and chloride ions. And if it's precipitation, we're going backwards. So, you know, what we're going to have is Q. Q is going to be greater than K, and it's going to force the reaction backwards. And so the way we do this is the initial concentration of silver ion is 0.100 molar. The initial concentration of chloride ion is 0.200 molar. Right? And so in other words, here Q is going to be way bigger than K. And so we need to shift this to the left. But what I like to do in a situation like this is we could do Le Chatelier's. This is going to be minus. Now, is this going to be minus S or minus X? This has got to be minus X. It cannot be S, because S is the maximum amount that dissolves, but what we're doing is X is the amount that's going to precipitate, not the amount that's going to dissolve. So this is going to be minus X molar. And so this is going to be the amount precipitated. And so at the end of this, we're going to have 0.100 minus X molar, 0.200 minus X molar. All right, this would be a Le Chatelier's type shift. Right, too much product, we shift it to the reactants. The way I like to solve this problem is I like to do this. Silver chloride is going to go to silver ions plus chloride ions. And so initially we start at 0.100 molar and 0.200 molar here. The way I do this is I reset. I'm going to reset. And so what I'm going to do is I'm going to precipitate out as much as I can. And then I'm going to see if some will dissolve. that is, go backwards. And so what I'm going to do is I'm going to reset this to the left. So this is going to be minus y, this is going to be minus y. And so what's the limiting reagent here? Ag. So this Ag is going to go to 0 molar, and the chloride is going to be at 0.100 molar. And so when I reset this, this is called a common ion type setup. Okay, now what I'm going to do is I'm going to allow it to change. You know, 0 molar, it's not going to be that way because a little bit of silver chloride will dissolve, right? And that little bit will be plus X or plus S. This is going to be plus S, the amount that dissolves in the presence of 0.100 molar chloride. And so this will be plus S molar. And so this is just looking at it differently. Rather than looking at the amount precipitated, we're going to look at the amount that will dissolve in the presence of this common ion of the chloride. And so I'm going to end up with S molar and 0.100 plus S molar. In other words, these two should yield the same equilibrium concentration. There's just different ways of doing it. Now, funny thing happens here. I want to precipitate out 100% of my silver ion. And what's going to happen is, no, I'm not going to get it. One way to precipitate out 100% of the silver ion is to increase the amount of chloride. The more chloride I have in here, the less silver ion that will dissolve, right? And so if I want to get out all 100% of my silver, how much chloride do I have to add? And so in order to precipitate would 6 molar do it?
No, I'm 12 molar.
All right, would 12 molar do it?
Yeah, I think.
You think so? So if I have 0.100 molar and I want to get rid of all 0.100 molar and I add 12.0 molar chloride, and then I do it my standard way, which is just to reset it. I just reset it so this goes to 0 and this would be 11.9 molar. Will that get rid of all the silver so I end up with 0 here or not? In other words, what I have here is this. KSP is going to equal the silver ion concentration times the chloride ion concentration. If I want the silver ion concentration to go down to 0, that means the chloride concentration has to go up to
100%.
not 100%. Infinite.
Oh, wow. Whatever.
And so is it possible to precipitate out 100% of my... No, it's impossible.
But how much we 12 molar?
Well, that's what we'll figure out. What is the percent precipitation with 12 molar HCl? Okay, and so this is how we'll set up the problem. Now, the resetting complicates things a little bit. With 12 molar HCl, what is percent precipitation? All right, so what that means is in this beaker, I'm going to make this 0.100 molar silver ions and 12.0 molar chloride. And so I'm going to avoid solution dilution. The solution dilution just means that we have to do an extra step. So if I said I'm adding 5 milliliters of 12 molar HCl, then we got to dilute it. But I'm not. All right, so this is the Le Chatelier's. The Le Chatelier's seems to be easier because here we go silver chloride. This is going to go to silver ion plus chloride ion. We start off with 0.100 molar and 12.0 molar, and we lose minus X molar, and so at the end we have 0.100 minus X, where X is going to be how much precipitates, and this is going to be 12.0 minus X. The problem is sometimes the precipitation is very near complete. That is, sometimes we get like 0.099999999 molar precipitated. If we get that much precipitated, what's your calculator going to do if it's more than 8 digits? It's going to round it to 0.1, which means 100% precipitation, but when we do the double check, we're off by infinite percent, right? And so that doesn't work. And so what we have to do for a lot of these calculations is we have to reset it, otherwise your calculator does round off error. And we get 100% precipitation, which isn't correct. And so what we'll do here is we'll reset the conditions, but it's going to make it a little bit more tricky in calculating the percent precipitation. So if we reset this, this is going to go to 0, this is going to go to 11.9. Right? And so the change here now is going to be plus S molar. And so at equilibrium, I'm going to have S molar 11.9 plus S molar. All right, now I know what my KSP value is. And so I can calculate what S is over there. And so let me do that right here. KSP was what, 1.8 times 10 to the minus 10? Is that right? Yeah, 1.8 times 10 to the minus 10. Which is going to equal the silver ion concentration, which is just S, times the chloride ion concentration, which is 11.9 plus S. All right, this is 10 to the minus 10, which means that, am I going to get much dissolving in the presence of common ion? No, and so I'm going to use the simplifying assumption here. This is going to be S times 11.9, which means that S is going to equal ten to the negative 11 molar.
That part.
Yeah, so we double check it. 1.51 times 10 to the minus 11 molar. And yeah, this is insignificant compared to this. So this is going to be 11.9 molar, roughly. And so we get these, we double check it to make sure it works out. Now, this isn't the percent precipitation. What we call this is the amount remaining. Okay, so S is going to equal, well, the solubility of silver chloride, formula units, which is going to equal the concentration of silver ion remaining in solution. So on the one hand, if we do Le Chatelier's, then the percent precipitation is easy. The percent precipitation is just X. X is the amount precipitated. So this could be X over the original amount, 0.100 times 100%. Right? That's easy. But when we reset, it complicates things because when we reset, we don't calculate the percent precipitation. Instead, what we calculate is the percent remaining. And so the percent silver ion remaining is equal to 1.51 times 10 to the minus 11. That's the concentration we're going to have at equilibrium with that chloride, divided by the original concentration, which was 0.100 times 100%. And so we calculate the percent remaining, which comes out to, this is 10 squared, so this is 10 to the minus 9. This is 10 to the minus 1, bring it up. So 10 to the minus 8. So this comes out to 1.51 times 10 to the minus 8%. Right? Which means that the percent silver ion that was precipitated is equal to this is going to be 100 minus this. And so 100 minus this is going to be 99.70. So 79. 1, 2, 3, 4, 5, 6, 7,
Bunch of numbers.
8, 4, 9%. Okay, this is different than this. If you did this on your calculator, you're going to get 100% precipitation. That's not correct, right? And 0% remaining. And so what we had to do is we had to reset this and do it this way, otherwise you're going to run into calculator round-off error. Does that make sense? And so this is why I prefer to reset.
Excuse me, I got 0.00001.5% precipitation. Is that right?
No, it's not right. The percent precipitated would be is equal to 100% minus the percent remaining. The percent remaining we just calculated is this. Here, and so that's it. And so without resetting this, we wouldn't have gotten any kind of reasonable answer to this. But you know, if that's the amount precipitating, isn't that essentially, I mean, how much remains? Just a tiny bit. You know, this is like 15 nanomolar remains, which is a tiny bit. And so to give this some perspective, we come up with an arbitrary cutoff. Because in order to get 100% precipitation, if we look at the percent silver remaining, with the addition of chloride, and so we'll increase the chloride concentration here. We'll start off with 0 chloride, so we at 0.100. What it's going to look like is this. It's going to approach 0 asymptotically, like that. And so maybe around here, we've pretty much got most of this out of there, right? Around here. And so we come up with an arbitrary cutoff. This arbitrary cutoff is this. The arbitrary cutoff is greater than 99.9% precipitation is, you know, 99.9% of this area is gone. Greater than 99.9% precipitation, we call it complete. Because are we ever going to get 100% precipitation? It's impossible because we'd have to go to infinite chloride. And so this means that less than 0.1% remaining is complete precipitation. And so we have to have less than 0.1% or greater than 99.9% precipitation. All right, so this gives us some calculations. So for example, did I really have to go 12 molar? I probably could have gotten complete precipitation with 6 molar, you know, or complete enough. Obviously, the more concentrated, the more I'm going to precipitate out, and the better. Okay, so this is just a start to chapter 18. Chapter 18, we're going to be looking at this, solubility.
12 molar is going to precipitate all of it?
What?
Is 12 molar is 0?
It depends on what you call all of it. If you call all of it greater than 99.9%, then yes. If you call all of it 100%, then no.
99.99 is greater than that.
And so we call it the complete precipitation. Is 12 molar going to yield complete precipitation? Yes, it is. You know, even less than 12 molar will yield complete precipitation.
That's why we added 6 molar HCl to the original solution, the cation solution.
Yeah. All right. Well, what this gives us is a way to use this. One of the uses for this is something called fractional precipitation. Fractional precipitation is this. Let's say you have chloride and bromide in the mixture. Both silver chloride and silver bromide are insoluble, so both should precipitate. But it turns out they don't have the same solubilities. one is less soluble, the other is more soluble. So is it possible to precipitate out the less soluble one completely, i.e. 99.9%, and leave the chloride essentially pure? It's not really pure, but as pure as you can. Is it possible? Well, that's called a fractional precipitation. So this is something we'll do next time, which is tomorrow. This is the next step of this. But today I need to talk about lab. And so let me bring up some stuff. We can take a short break, and then I'm going to put the lab up on the projector here.